Lesson 12.2 is titled Conditional Probability. Again, we're going to be working with probability of different types of events. Conditional probability is defined as two different events. Event B will occur given that event A has already occurred. So one is conditioned based on the outcome of the other one. The notation would be B and then kind of /A, meaning B can occur because A has already happened. Let's see how this works with a big example over here on the right. Example 1. A student committee is formed to decide on how after-school activities will be funded. The committee members are selected at random from different clubs. The frequency table shows the current club members' data. We have sophomores, juniors, and seniors, and there are students that are in drama, science, and art. It says, what is the probability that a junior is selected at random from the committee? All we have is one instance happening. A junior is selected. That means we would need our event and then the total. So we would say the probability of being a junior that's selected. In this group, we see there are a total of 40 juniors, all in that row. That means there are 40 events that are likely that we want to happen. The total number of students that are possible to be selected would be down in the bottom, that 115. And that fraction reduces down to 8/23, or just about a 25% chance. I said 23rds and I wrote 24. Sometimes that happens. There we go. 8/23, or like I said, about a 25% chance. Now let's change up our probability scenario to use this conditional probability. Example B. It says, what is the probability that a member of the art club selected at random is a junior? This means the art club group has to be selected first, and within that group, what's the probability that we would have selected a junior? We write that out as B/A. So a junior was chosen from the art club. Now it's not guaranteed that we use that 115 anymore, or we even use the 40 for the number of juniors. The art club participants have a total of only 58. That's going to be what has already happened. Based on the fact that we know somebody from art club is selected, what's the probability that they were a junior? Well, there are only 16 juniors that are in the art club. That would be the number of events we want to have happen. 16 out of 58 will reduce to 8/29. Based on example A, this outcome is less likely. It has a bigger denominator, so the fraction has a smaller output value. Let's see if we can work through just two more. It says for part C, what is the probability that a member of the drama club is a sophomore? Again, we're not looking at all the possible ways this can happen. We're just trying to figure out within this scenario, what is the probability? So now we want to figure out, knowing that a drama club student was selected, what's the probability they were a sophomore? So we'll put sophomore selected out of the drama club participants. Now the drama club, let's see. Oh, there's only 17 students in drama. That would be our possible group to select from. And there are only 3 sophomores, so 3 out of 17. All right, try the last one. What is the probability that a sophomore is a member of the drama club? When we ask this in reverse, it does change up how we write out our probability. So what is the probability that a sophomore selected was a member of the drama club? That means the sophomore condition is first. The fact that they would be in drama club is the second factor. As we switch this around, drama club participant that we know came from the sophomore class. Now the total number of sophomores is 36. But there are still only 3 sophomores in that group. 3 out of 36 reduces down to 1/12. That's definitely less likely than being a drama club member and being selected as that sophomore. All right, let's change gears and try a different type of example. Example 2A. A band's marketing agent conducted a survey to determine how many high school fans the band has. What is the probability that a surveyed student plans to attend the band's concert and is a fan of the group? So let's take a look at the values over here on the right. Students who plan to attend the concert. It says 70% of students who plan to attend, out of them, 80% of those students are fans. So maybe the other 20% are going because their friends are going or something. Students who do not plan to attend, there's only 30%. And of those 30%, 25% are fans of the band, but maybe they have a math test the next day. The other 75% are like, yeah, I don't really like that band, so I'm not going to go to their concert. All right, what are we looking for here? What's the probability that a surveyed student plans to attend and is a fan of the group and represents something specific in this scenario? Now, since we're given percentages and not total number of students or fans to work with, we'll utilize those percentages kind of like the percent chance of rain in yesterday's lesson. The fact that we want both events to happen means we're going to multiply these together. So the probability a student attends and is a fan, we find by taking the probability that they're attending, which is 70% or 0.7, times, out of those 70%, 80% are actually fans. So what is the probability that a randomly selected student who's at the concert is actually a fan of the band? Believe it or not, 0.7 times 0.8 is only 0.56. You would have a 56% chance of randomly selecting a student who planned on attending and they liked the band. All right, the last one for this page. Flipping things around just a little bit. What's the probability that a surveyed student plans to attend but is not a fan? They're like, nah, I don't know, I'll just go, something to do. So we want them to attend but not be a fan. All right, so the probability that they'll attend and not a fan. Let's take a look. Well, the attending students are 70%, so that would be 0.7. And we know that 80% said they were fans. So out of that cluster, 20% would not be fans. So then I'm going to multiply this by 0.2. This probability is significantly smaller, 0.14 or 14%. You'd have a 14% chance of randomly selecting a student that said, yeah, I'm going to go, but I don't really like the band. Our final group of examples looks at probability with a standard deck of cards. We'll look at what it means to be independent events, and then we'll look at what it means to be dependent or have conditional probability. It says find the probability of drawing the given cards from a standard deck of 52. We're going to do one with replacement and then one without replacement. With replacement means you pick a card, you put it back in the deck, and then you pick a second card. Without replacement means you pick a card, set it off to the side, and then pick your second card. That will change the probability. Let's take a look at some examples. It says find the probability of drawing a club and then a spade. So in part A, we're going to draw the club, put the card back, and then we want to draw a spade. These would be independent probabilities. So we would want the probability of getting a club and drawing again, probability of getting a spade. And means we would multiply them together. Now in a deck of cards, there are 13 clubs out of 52. That means there's a 1 in 4 probability that you would pick a club, 13 out of 52. And means multiply. There are also 13 spades out of 52, which would also be 1/4. The probability that you would pick a club, put it back, and then pick a spade is only 1/16. That's a pretty small decimal. Let's see what happens if we pick our first card and then we put it back, we don't put it back before we get our second card. So the probability of getting a club and then a spade without putting that card back, without replacing it. Our probability of getting a club is still going to stay 1/4. That doesn't change. But now our probability of selecting a spade with the cards that are left over is slightly modified. There'd still be 13 spades, but now there are only 51 cards instead of 52. That changes our value, which would be 13 out of 204. See if you can try the next problem. A queen and then an ace. Once you think you have it, press play and see how you did. All right, did you get 1 169th and 4 663rd? The queens in the deck are different than the number of clubs or spades in the deck. There are only 4 queens. Therefore, 4 out of 52 reduces that fraction or probability to 1/13. And then if you put that card back and you want to select an ace, again, there are only 4 aces. You'd have a 1/13th chance of selecting that card. The probability that you could do both events in a row would be 1 out of 169. That's a very small probability of happening. If we pick the queen and set that card down, that means there are only 51 cards left. There are 4 aces, so the second probability changes slightly to 4 out of 51. Multiply those two fractions together and you have a 4 in 663 chance of getting a queen and then an ace. All right, how about a face card and then a 6? Well, here's where we have to think about, okay, face cards in the deck. A face card is a jack, a queen, or a king. They all have faces on them. So there are a total of 12 face cards in a deck. And I think we talked about that before. And then we want a 6. All right, so let's see. Probability, this is part A. Probability of a face card and followed by getting a 6. Well, there are 12 face cards in the deck. 12 over 52 would reduce down to 3 over 13. Times the probability of getting a 6 would be 4 out of 52 or 1 out of 13. So this is going to be a pretty small answer again. 3 times 1 is 3 on top. 13 times 13 is 169 on the bottom. 3 1/69ths chance of getting this scenario in your probability. And again, if we change things up, we'll have 3 out of 13. Whoops. Hang on. Sorry. We'll write it out first, and then we'll write out our probability. So our probability of a face card, we set it aside, and then we pick out our 6. There we go. So our first probability, again, never changes. That's going to stay as is. But then our second probability becomes 4 out of 51. And this would become, well, actually, we could reduce this. The 3 goes into 51 17 times. Well, that's kind of nice. That would give us a total probability of 4 out of 221. Now, if you didn't recognize that and you multiplied them together, you could reduce that fraction down to 4 out of 221. All right, our last example. Whoa, this is a good one. We want a king, then a queen, then a jack. We want 3 events happening. That's crazy. With replacement, meaning we put our cards back, that means each probability is unique. So if we want the probability of getting a king and putting it back and then picking a queen and putting that back and picking the probability of picking a jack. There we go. But there's only 4 kings, 4 queens, 4 jacks total. That means the probability of getting each type would be 4 out of 52 or 1/13th. We're going to multiply 1/13th times 1/13th times another 1/13th. Not very likely. You have a 1 out of 2,197 chance of getting that situation for your probability. Finally, watch what happens if we get our king first. We don't put it back, but then we try to select again and get a queen. We don't put that one back, and then we select our jack. I keep putting the P before there we go, the probability of getting a jack. Our first scenario stays as is. 4 kings out of 52 would be 1/13th times, but now the queens will differ slightly. There are only 4 of them out of 51. Then it even changes for the jack. If we don't put that queen back, there are only 50 cards left. And there are 4 jacks, so 4 out of 50 would be 2 out of 25. Check out this probability. If we multiply the numerators together, 1 times 4 times 2 is 8. All over, 13 times 51 times 25 is going to be 16,575. That looks like it's the least likely option of all of these with a standard deck of cards. There's lesson 12.2. Again, we won't have a homework assignment for this lesson. Just send me a picture of your notes.